My name is Tania de Monte Gonzalez. I'm a PhD candidate in the Mechanical Engineering Mechanics department. And today I'll be talking about nonlinear hydrodynamic modeling and control of wave energy converters. There we go. All right, so we all know by this point that we need to transition from conventional energy methods to renewables. The goal is to reach net zero by 2050, and so there is a lot of research and money being put into investigating different renewables. This image here shows the technical potential power that the marine energy or the marine renewables have for generating electricity. This number might not mean a lot to you, but it's equivalent to around 57% of the total energy generated in the US in 2019. So there is a great potential here to harvest wave energy or marine energy. And there are devices that are called wave energy converters that are used to harvest this energy. In my dissertation, I talk specifically about one type of wave energy device, which is the heaving point absorber. This heaving point absorber, it's basically like a buoy that floats in the ocean, and it converts that energy from the waves making the buoy float, move up and down into some sort of useful energy. That useful energy can be electricity, right? But it can be many different types of energy. The system that converts the energy from the mechanical to electrical in this case is what's called the power takeoff system. You're gonna hear me talk a lot about PTO or power takeoff. That's the mechanism that converts the energy. Now, this mechanism can convert energy, so function as a generator, but it can also function as a motor or as an actuator. If you invert the current, you can put energy into the system and control it. And so the way I'm going to be talking about the power takeoff system is both ways. I'm going to talk about it as a motor and as a generator as well. Now, why do we not see these devices in the ocean yet? Well, there are many challenges, as you can imagine, with having devices in the ocean. It's a very harsh environment. It's very expensive as well. All of these are just a few of the challenges, but it really all comes down to a very elevated levelized cost of energy. Pretty much very expensive energy. That's what it means. And so the main goal, the main challenge and motivation for my research is to try to reduce this levelized cost of energy. There are many different ways of reducing this levelized cost of energy, but my focus is in advancing the controls. And what this is gonna let us do is improve the energy production. By improving or by generating more energy, we reduce the cost of the energy that we're generating. I'm gonna separate this presentation, like Dr. Parker said. I'm gonna be talking just a little bit about what my dissertation is about. I'm gonna separate it in two parts. The first part is the modeling and validation. For any model-based control, you need a model, a mathematical model. So that's the modeling that I've developed. This is the paper associated with that. Now, the content I'm showing in this presentation is only my contribution to this paper. This paper has a lot of other things that are not covered in this presentation. But what is shown here is my contribution to that paper. And what this paper or this contribution adds to the research nowadays is it provides an algebraic nonlinear Froude-Krylov force derivation. It's a closed form solution of a nonlinear force. Then it provides a change of coordinates of the limits of the integration. This is something that hasn't been done before. And this is mostly to accommodate for some boundary conditions that I'm gonna show you in a little bit. And finally, and I think this is one of the most important parts of this contribution, is the validation against experimental data that was taken here at the Wave Tank at Michigan Tech. So that's the first part of the presentation. The second part is in the controls. So once I have the model, once the model is validated, I move on to the control side. And for the controls, I'm presenting the novel, the nonlinear model predictive controller. that incorporates these nonlinear Froude-Krylov forces. So this model incorporates the nonlinear Froude-Krylov forces, which hasn't been done before. And it also provides a comparative analysis between performance, so power performance, and the difference in like linear and nonlinear MPC. MPC is model predictive controller. So basically the idea is it worth it having a nonlinear model predictive controller? So the presentation outline is gonna start with the modeling and validation. Then I'm gonna move on to the controls. Then I'll show the results of the controller, and finally the conclusion. After that, I will open the floor for questions. All right, modeling of wave energy converters. There are many different ways that these wave energy converters can be modeled. And right now, when I'm talking about modeling, I'm talking about the specific one of point absorber that my dissertation is about. All of these different methods for modeling wave energy converters come associated with a computational cost and with an accuracy index, that I'm gonna be calling fidelity. So fidelity indicates how accurate the system is. The higher the fidelity number, the more accurate the system is. So if we see here, for example, real time, for us, or for me, at least in this research, is very important because my main goal is controls. So I need to be able to have a model that I can run in real time so I can control a system in real time as well. Linear models do that very well, but then as you start including nonlinearities in the system, you see it becomes more computationally expensive. It becomes more accurate, but it is also more computationally expensive. So my research falls in this category where I'm using a hybrid method. That means that I'm using linear theory, but I'm also incorporating some nonlinear terms. And by incorporating the nonlinear terms, I'm moving the fidelity of the linear model further into the more accurate side. And it's increasing in computational time as well, but I'm still at the real time level. And that's what, I'll go back. And that's what I'm gonna be calling algebraic nonlinear Froude-Krylov force. So that's the contribution of this work. All right, so the main equation for a wave energy converter that I've been implementing here is using Newton's second law. So mass times acceleration equals the sum of the forces. The first two forces that I have here are the Froude-Krylov force. And I have separated them into two different Froude-Krylov forces. One is the static, and the other one is the dynamic. The static Froude-Krylov force is equivalent to, some of you might know as the buoyancy force. So if you have a buoy, you can imagine a ball, and you have a still water and you push it down, you're gonna feel a force pushing it up, kind of like a spring force. That's the buoyancy force. That's the Froude-Krylov static force. Now the Froude-Krylov dynamic force is the force that the buoy experiences, also due to the water, but when there are waves. So there is no, it's due to the incoming wave, not to the still water level. Then we have the diffraction force. This is the force due to whenever you have a buoy or any sort of device in the water and there are waves coming in, you will see that behind the buoy there is a wave that gets diffracted. This force is accounted here in this term. Then we have the radiated waves. That's when the buoy, if you push it down, if you picture still water, you push it down, it's gonna radiate some waves. That's the radiated force. And then finally, and this is one of the most important forces in this work for me, is the PTO force. So remember, this is the force that actuates the system, and it also acts as the force that is generating energy as well. But the context here of this force is the force I'm gonna be sending to the system to control the wave energy converter. And this is an schematic of how not very realistic, but you get the idea. Now this picture shows, this bar shows the contribution to the total hydrodynamic forces of each of these terms. And as you can see, the first two here are the Froude-Krylov terms, and they are the ones that contribute the most to the total hydrodynamic force. And that's the main reason why we figure it's important to model these forces as accurate as we can, because they are the most significant in this sort of wave energy converters. How do we derive the nonlinear Froude-Krylov force? Give me 1 second. I want to start the clock because I don't know how long I'm taking here. All right. So the Froude-Krylov force is derived by integrating some pressure equation over the surface area of the buoy, or not just the surface area, but the wetted surface area. So the area that is under the water. The way this is done in linear models is that it considers like the field, the wave field is constant, and the integration happens across that constant wetted surface area, which is usually at the equilibrium point of the buoy. In the nonlinear model, I'm considering the instantaneous wave elevation and the instantaneous buoy position as well. So that's gonna also change how much of the surface area of the buoy is wetted. So in order to derive the method, I need some pressure equation, and this is the linear potential flow theory pressure equation. It's also known as the Airy's wave theory, and it's divided into the two parts as well, dynamic and static pressure. And it comes with some assumptions. So because it's a linear potential theory, it's gonna assume that the buoy motion is small. It's also gonna assume that the wave stiffness, so like the slope of the wave in comparison to the diameter of the buoy, is not significant, so it's not steep. And then finally, this is one of the boundary conditions I talked about for my contribution in this work. This linear wave theory has to meet a lot of boundary conditions. I'm pointing this one out specifically because it's the one important for my derivation. And this boundary condition says that at the still water level, meaning that Z, so the position of the buoy is equal to 0 at equilibrium point, the pressure at that point is 0, and above that point is also 0. So what that means is that when you do have some sort of wave elevation, this theory, if that wave elevation is significant, it's very inaccurate because the pressure above that point is not 0. So I'm gonna account for that to account for the wave elevation when it's farther up that equilibrium point. All right, and the Froude-Krylov force is then defined as the integrals of this pressure over some sort of shape. So this shape can be any sort of shape that you have, as long as it's an axis symmetric buoy, or an axis symmetric shape, as long as you can revolve it around one axis. You can have any sort of profile here. The one I'm gonna be showing is for a sphere. And yes, the one it's shown in this contribution is for a sphere, but it can really work for many different shapes. As long as you have this line in red, you're good. So here's the Froude-Krylov equation again. I have the pressure. Now I need to figure out what is this profile of revolution of my, well, the profile of revolution is known for different shapes, specifically for a sphere, that's known already. What I need to figure out are the limits of integration. So the limits of integration are gonna tell me the wetted surface area. So if you see here, the wetted surface area goes from minus HO, this is the draft of the buoy, minus HO to 0. I'm keeping the upper limit of integration at 0, which is the boundary condition I talked about. Now this will be the linear theory. This is how in linear methods is calculated. But now if the buoy is moved up or down, it doesn't matter. You see that the wetted surface area changes. And so the limits of integration are gonna change now from minus that draft plus that Z displacement of the buoy. And now if we add the wave elevation, it's also changing again how much the weighted surface area is. And so now I'm gonna integrate from minus the draft plus that displacement plus or minus for the sign convention, the wave elevation. And keeping in mind here, all of the upper limits of integrations are equal to 0. That's so that we're still meeting that boundary condition. And that's something that a similar method was done before of using an integration. So this like volume method to calculate the instantaneous weighted surface of the buoy. But this consideration of this boundary condition was not taken into account. So this is, again, this is what the contribution is for this work. Now that we have this model, we need to validate it. Otherwise, anybody can come up with a mathematical model and you don't know if it's right or wrong. So to validate it, we tested at the Michigan Tech wave tank in the sub-basement here. This is a spherical buoy. It's about, it has a 10 centimeter radius, so it's really tiny. And it's fixed to this dyno that it's keeping the buoy in place, and it has a load cell right here that measures the force. So as right now in this position, for example, when the water is not moving, that load cell is reading 0. That's the equilibrium position. As soon as we start sending water, waves to the buoy, that load cell is gonna measure how much the force is changing due to the waves. So by keeping the buoy fixed, the displacement, velocity, and acceleration of the buoy are 0. So it makes the Newton's second law equation that I showed, it makes that much easier, and we're only left with the Froude-Krylov forces and the diffraction force. From this load cell data, I got what I call the experimental data. So this, when I say experimental data, is the load cell data. And then I compare it to my numerical method. So first I compare it to my work, this algebraic nonlinear Froude-Krylov force, and then I compare it to 2 more models. I compare it to this Wheeler stretching method. This is a higher accuracy, more computationally expensive. I just wanted to see how it compares to different models. And then I also compare it to the linear potential flow method model to see if it performed better or not. So in total, I have 4 sets of data. I have the experimental and these 3 numerical models. To assess the accuracy of the models, I use this fidelity index. And this fidelity index, if you look at the equation, you don't have to look at all the equation, but these parentheses here, it has the error between the experimental data and the model data. So it's pretty much assessing how far or how close to your experimental data you are. And this is just one of the results from that. This is for a wave that has a frequency of 6.28 radians per second, or 1 hertz wave. And I have 3 different amplitudes. The first one is at 10 millimeters, and then it increases to 15, and then it increases to 20. In the first one here, you might notice there is not much difference between the experimental data and the models, which is good. That's a good thing. But what I'm trying to assess is like, I'm trying to assess the nonlinearity. So the nonlinearities are gonna become more relevant when we have higher waves. And so if we go down here to the 20, we see already the linear model, which is in blue, is starting to look like it's not as accurate anymore. And then the other 2 were higher fidelity, so they're working very well in that case. So I have here the fidelity index for 3 different frequencies. And this is for wave amplitude 10, so the case where the waves are considered small. You can see the fidelity index is very even across the 3 different modeling methods. So that just confirms that the linear theory works very well for small motion. Now, when we have small, bigger motion or bigger waves or bigger buoy motion, the linear method starts to fail. So it starts to become less accurate. and the nonlinear algebraic Froude-Krylov force that I derived is pretty good. Of course, here it starts. This case. It starts to become less accurate because also the wave stiffness for this buoy was becoming too aggressive, and the theory fails also when the wave stiffness is not small. But yes, overall, the fidelity of my model is pretty good. And so I was like, okay, I have a working nonlinear model. Now I can go ahead and start working on my controller. Okay, so I'm working now on the model predictive controller. So why do we want to use controllers where it has been shown that using some sort of control mechanism in these wave energy converters can increase the amount of energy production? AEP, I forgot to put it there, is annual energy production. It can increase it up to 200%. So it is a significant increase of energy that we can get by implementing any sort of a strategy, control strategy. Here I have put some control strategies in the literature, not many, and I don't intend for you to understand this. It's just to give like a big picture of like the variety of control strategies that there are. Now, what happens when you implement a control strategy in wave energy converters is that you increase the motion. Usually you try to amplify the motion of the buoy. By amplifying the motion of the buoy, you're making the nonlinearities more significant. So that gives us ground for saying, okay, we need this nonlinear model. Otherwise, we know we're not modeling right. MPC, model predictive control, is a great option for a system that has nonlinearities. Not only is good with nonlinearities, it's also an optimal controller. So I can generate or set it to generate optimal energy. And I can also subject the system to constraints. And that's very important in wave energy converters because you don't have unlimited power takeoff power, like PTO power from any sort of mechanical system. So you can constrain the limits of that PTO system. And you can also constrain the displacement of the buoy so that it doesn't go off the water or it doesn't go completely submerged underwater if that's not something that you want the buoy to experience. Now, because it's a very good option for controller, it has been studied a lot in this field. There are many papers about model predictive control in wave energy converters, but most of the papers don't consider nonlinearities in the model. You can see here, most of them have linear time invariant or linear time varying systems. Only out of the ones that I saw in a literature review, only 12% of the optimal and MPC controllers consider nonlinearities. And these nonlinearities are not specifically to the modeling. It can be nonlinearities related to other things like PTO efficiency, for example, not directly related to the model dynamics, and even less related to nonlinear Froude-Krylov forces. So this is the same paper that I showed at the beginning. This is my contribution for the controller, for the control side of my presentation. Nonlinear model predictive control that incorporates these Froude-Krylov forces. What is model predictive control? Well, it's an optimal controller that predicts the future behavior. That's why it's predictive. It predicts the future behavior of the system, and it adjusts the input. In my case, that input is the PTO force, or also called the control force. It adjusts the inputs while keeping the buoy within the constraints that you set on the problem. And there are three main parts to formulating this problem. The first one is a model-based controller. So you need a mathematical model of your system. And that's what I developed in the first part of this presentation. I'm going to be using the same equation here. The second part is an objective function. So what is the goal of the controller? The goal here for me is to optimize energy generation. So the energy absorbed in wave energy converters can be expressed as a the force of the PTO system times the velocity of the buoy, the integral of that as well. And so what I want to do, this is an optimal problem. So I'm going to have an objective function that I'm going to try to minimize. And so because I want to maximize this, I'm just going to minimize the opposite of this. So that's why the sign changes there. So my objective function is, again, the sum of the PTO force times the velocity on that prediction horizon. And I'm going to show you now how the model predictive controller works in a more graphical way. And then the third part of this MPC is the constraints. The good thing about MPC is that we can set constraints on the control input, so on the PTO force in this case, and on the states of the system. I chose to put a constraint on the displacement of the buoy. So I have a constraint on the displacement, and my constraint here is just saying I don't want it to get off the water and I don't want to be completely submerged in the water. That's my constraint. And then this controller max force is just so that it's just a way of saying you don't have unlimited power that you can put into the system. So I'm just limiting it to that. Now this is how it works. First, we start here at 0. And then you're going to predict the future behavior of the system based on the mathematical model that you have. You're going to predict it over a prediction horizon. In this case, that prediction horizon is 3 seconds. So based on this predicted behavior of the system, you're going to use some sort of optimization algorithm to optimize the control force. So this line in blue up here, that's the optimized control force. Once you have that, you can implement that in the system. And that's here the red line. It's implemented in the system until you want to re-optimize. In this case, that happens after 0.6 seconds. Here I'm saying, okay, I want to re-optimize. And so here you look ahead again, another 3 seconds. So now it goes to like 3.6 seconds. It looks at the predicted behavior of the system and it optimizes that PTO based on that. And so on. You keep going, you implement that until the next optimization time and then re-optimize, re-implement, and so on. It's an iterative process. But as you can imagine, there is a lot of optimizations that are happening, especially depends on how often you want to re-optimize, is how many, or how computationally expensive this method is. So here we have the schematic of the controller. Here I have the WEC plant. WEC is the wave energy converter plant. Now the plant is always nonlinear. This is what I'm considering my truth model. And when I talk about nonlinear model predictive control, is the model that the model predictive controller is using. So this model is what's changing, in my case, from nonlinear and linear. So what I'm gonna assess in this work is if it's worth having a linear, or if it's worth having a nonlinear wave energy, a nonlinear WEC model there. So the nonlinear model here is the one that incorporates the Froude-Krylov forces that I derived. And the linear model is a linearized version of that. And it's linearizing it at the z = 0 equilibrium point. And here is just an image of how different these Froude-Krylov forces look like. Then this is under control conditions. But the difference between the nonlinear and linear can become very significant, and that's gonna affect on how the controller acts as well. I simulated a range of different waves. So I have from 1 to 2.5 meters in wave height, and the period is from 6 to 9, and these are irregular waves. So irregular waves are composed of many different frequency waves. It's not just a singular sinusoid. Now, this is a real scale simulation. So I have a buoy that has a diameter, the diameter is 5 meters, the radius is 2.5. So I don't know if you can picture the size of that. It's humongous. It's very big. And that's why also the forces, if you notice here, are also very large. I'm talking about kilonewtons. And the mass and the buoy natural frequency is 2 radians per second. Finally, I need to point out what assumptions I'm doing when I'm designing this controller. The first assumption is that I have full knowledge of what the waves look like at the moment and throughout my prediction horizon. I assume that I know what the wave is. I'm not doing any sort of wave estimation or wave forecasting. I assume I know that. The second one is that I assume I have a perfect PTO system, is 100% efficient. I'm also not considering the PTO dynamics. I'm just calculating how much the PTO force should be without considering the dynamics of that. And finally, this controller is not really meant to be implemented in real time. This controller, my work, is mostly to assess if it's worth having a nonlinear model in the MPC controller. Because if we come to the conclusion where it's not worth it, then it's not worth also investigating real-time applications of it. So this was the first step of that. Now I'm showing here just one wave case result where I have the energy absorbed of the buoy. In red is the nonlinear energy absorbed, and then in blue is the linear. And as you can see, the nonlinear outperforms the linear. And in fact, in this case, it's 44% better than the linear. And here I'm showing the PTO forces. The PTO forces, remember, were constrained, and the constraint in this case was of 300 kilonewtons. And the constraint is being met very well in both controllers. Like the MPC controller is really good at keeping that control input constraint. You can also see some peaks here. That happens every time I was re-optimizing. Those peaks in the force can happen, but it doesn't really affect too much on the dynamics of the system. It doesn't affect the buoy displacement that much. I'll show you in a little bit what can happen. Now, to assess this difference between linear model and nonlinear model, I calculated this power difference in percentage, and I have all this information here for you. So let's go one by one. So I have 4 different controller configurations. The first one here has a prediction horizon of 6 seconds. So I'm looking into the future 6 seconds, and it's re-optimizing every 3 seconds, okay? This one here is also a 6 second, but I'm re-optimizing every 6 seconds, right? So it's optimizing less often than this one. Now, the 2 cases down here, I extended the prediction horizon to 12 seconds. So it's a much longer prediction that you have of the system. And I also have the optimization time to 3 seconds and to 6 seconds. Now, I'm going to talk about that specifically, about these controller configurations in the next slides. Now, let's focus on if the nonlinear model is worth it or not over the linear model. So here you see it's color-coded. Blue means the linear model performed better. It got more energy. Red means the nonlinear model got more energy. And the numbers are percentages. So here, for example, in this case, at 1.5 meters in 6 seconds, this is the case that I'm showing there, the nonlinear model generated 44.6% more energy than the linear model. And if you just look at the big picture from back there, you see mostly red. You see mostly the nonlinear model performs better, generates more energy than the linear model. Overall, if you just look at the big picture, you can say, yes, it's better. But there are some cases where the linear model is working better. So first point, overall, it looks better. Second point, here, where we do have some linear models working better. What happens in those cases is that the limit, the constraint on the displacement that I have set is not being met for the linear model. If you look at this picture here, the linear in blue I don't know if it might be a little bit hard to see for you. The black line is the limit, and the linear model is exceeding that limit. And it's exceeding it there, in this case, here, 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 in many different places. And because it's exceeding it, the motion is bigger and you get more energy when it's bigger. But the point was to keep it constrained, and ideally for a reason, right? Let's say that was you're constraining it to the PTO stroke that you have of your system. If you're not predicting it well enough so that the system is hitting the end stops of that actuator, then you're causing a lot of damage to the PTO or to the system overall. And so exceeding these limits is really not a good thing. And in this case, it might not be too significant, but it wasn't that many of the cases where that happened, really. Actually, it wasn't that many of the cases where the linear model performed better, but there are a lot of the cases where the linear model did not meet the displacement constraint. And that's because it was off. The predictive model is clearly off from the actual model. And so, yeah, it gives the wrong or like an overestimated controller input to the system. And then here, what I'm saying is when I'm optimizing every 6 seconds, these two cases, it's always better when you have a nonlinear model. There is no case where the linear model was better. Now, this is just performance difference. It doesn't tell us how much power we got out of it. It was just comparing linear to nonlinear model. This is how much power we get for the 4 different controller configurations. So we have this one, the first one, that has a prediction horizon of 6 and an optimization time of 3 seconds. This one is the one that performed the best. And you might think, okay, let's look at this one. This one, you have a prediction horizon of 12 seconds. So you know further in the future what the system is going to be doing. Why is it not performing better? You might think that. That's what I thought when I was working on this. I thought, okay, larger prediction horizon, you know better, you can optimize better. Wrong. It's not, it doesn't work like that. It reaches a certain point where the prediction horizon, if you keep increasing it, you're just increasing the computational expense of your system, and it's not generating more energy. No. But I do want to say that if you decrease this prediction horizon a lot, if let's say my prediction horizon was 2 seconds instead, then you can reduce that energy production by a lot. So it kind of looks like a step, not like a ramp function that then settles to a point asymptotically. That's how it looks like as you increase the prediction horizon. It can be very bad at the beginning, but then it reaches a point where it's the same. And then if we look at the optimization times, here we are re-optimizing more often than in this case. And the power is better. Even in these cases, the power is better when you re-optimize more often, which makes sense. But it's also a little bit similar to the prediction horizon, to where if you re-optimize too often, so if you re-optimize, let's say, every 0.5 seconds, it doesn't become better for the amount of computational load that you're putting into the system. So there's always like this trade-off. Are you ready to talk about that? So I'm gonna move on to the next one, where I'm showing I made this nice transition so that you can remember what the last slide looks like. This is the computational expense of each of the controllers. This case was the one that performed better, so more energy, but it's also not the most computationally efficient. This is the most computationally efficient. That's because we have the 6 seconds prediction horizon time. So it's out of these two, it's the shortest. And then it's re-optimizing every 6 seconds instead of every 3 seconds. So this one is the fastest. And it also, you can see here, if you compare linear to nonlinear models, they are about the same. So in this case, you don't even have the trade-off of computational expense for using a nonlinear MPC. You have about the same computational time, and the nonlinear MPC performs better. If you remember the case here for the table, it was all red. So the nonlinear MPC in this case works better for all of the cases. So there is really no trade-off in this case. And then this case is the one that is more computationally expensive, which makes sense as well because we have a very long prediction horizon and it's re-optimizing every 3 seconds. So it's re-optimizing up. Now I want to make it easier for us to compare. So now I have all the metrics and I'm only choosing the prediction horizon of 6 seconds. I figured that was one of the best cases. So I'm only showing the differences for this prediction horizon of 6 seconds and the 3 plots on the top row is for the optimization time of 3 seconds. And down here is for the optimization time of 6 seconds. So in terms of power, this one is better. This one, it's okay, but it's not better than this one that we are re-optimizing. And if we compare the computational expense, this is more computationally expensive than this one. Now, that would be up to the user, I guess, or whoever is working with an actual system to say, okay, like I can only handle this much computations and I'm good with generating this amount of power, and that's valid. If you can handle, thank you. So to conclude this work, I'm gonna go over a little bit of what I talked about for the past 40 minutes or so. So accurate models are crucial for the development of model-based controllers. And this work presented the development and validation of this nonlinear accurate Froude-Krylov force. And it demonstrates superior accuracy and it's better than the traditional linear models. And then the second part that relates to the controller, I have the nonlinear model predictive controller that has this nonlinear Froude-Krylov force that you saw were very significant when it comes to the total hydrodynamic force of the system. And it also improves the power generation across different conditions, most of them. And it also, well, the last point here is kind of like the main reason of why we're doing this. The main reason why we're doing this is to optimize the system, generate more power, reduce the amount of money that it costs to generate power with marine energy. Here I have the contributions. These 2 bullet points here are the 2 that I talked about on this presentation. They are both in preparation, so I haven't published them yet. But I will be publishing them and I can send them your way once it's published if you were very interested in this topic. And with that, thank you. I would like to thank Dr. Parker for being a great advisor during all this time. Thank you so much. My committee members, Dr. Weaver, Dr. Meadows, Rick, thank you so much for being here all the way from Colorado. All the way from Colorado. And Dr. Masood, that hopefully will watch this online. Thank you for your support, for your reviews, for your comments. I really appreciate it.